we get started, first, we are going to try having the class on Monday, Wednesday, and Friday in Dick Building Room 209. So tomorrow for class, we won't meet here. We'll meet in the Dick Building 209. All of our Tuesday activities will be here. So the Tuesday class, 11:30, will still remain here. And the Tuesday labs, of course, will remain here. Clapping about which part, Brady?
No, that's
just quivering. Okay.
This is like from here on, though?
Well, unless they kick me out of that classroom, but or things go wrong, who knows? But we'll see. So it's the plan, at least for now. Okay, we are going to today talk about calculating the pressure as a function of depth, something that's very simple. Doing it with a calculus way, it's still very simple. And then we're going to calculate the torque created by water on a dam. I got these two pictures. This one here is written in the arcane way of physicists. And, it's old because these days we try to write things in ways that are easier to decipher. But this is talking about the calculation of, how the pressure changes as a function of depth. And the fact is the density of water is not constant. And so over here you have something for the density not remaining constant. For our purposes, we're going to treat the density as constant for the dam. I actually looked into doing it more technically and decided against it. This picture here, I put in for a completely different reason because I thought it was kind of interesting. Number one, it shows a little more details about how a dam is made. Number two, it's actually from a military explanation. So what this is a dam buster bomb. And they launch the bomb at sea level with a backspin. And so you see that launched bomb is bouncing along the water, or sea level, water level, bouncing along the water until it hits the dam. But because of the backspin, when it hits the dam, it rolls down the dam. And then it detonates down there and cracks the dam somewhere low. Why do they want to break the dam down here and not at the top? Yeah, you break it down here, you have high water pressure, it's going to be destroyed. You break it up to the top, the water pressure is not so high, maybe they can salvage it. Right? Now, of course, I'm not into being destructive. I get really annoyed when I see people who are angry or happy and they decide the best way to show their happiness or anger is to destroy something. So, flip over a car, start a business on fire, steal all their goods. That's not the way to celebrate or to show that you're angry. Neither is breaking somebody's bridge or a dam. I do like the picture, though. You can see that inside the dam, they build up against that base. Outside the dam, you have this big piece here. And you can see that it's buttressed by a piece here as well. Why would they have to do that? We have a number of students who are in statics class now. From your statics class perspective, or from a week and a half ago physics class perspective, since we covered statics in 2 days, why do they have things like the buttress on the back of the dam?
It looks like it's a reinforcer.
Okay.
There's a lot pushing against it.
There's a lot of force pushing out because of the water pressure.
And so it's going to apply it opposite.
So it's going to apply force opposite. Why do you suppose you have that clay bank in there?
Reduce the water pressure that's directly against the base of the dam.
Okay, there is reduce the water pressure, but there's another thing too. What direction is the force going to be created by the water on that clay bank? It's going to be creating a force that goes like this. And notice the dam is curved back into it. So it's anchoring it a little more, using the water pressure to hold that base in place a little more. Right? The guys who build these things, the engineers who design them, they are nobody's idiot. Right? They're trying to take advantage of everything they can. What are the concerns that you would have about building this dam? I mean, this dam, any dam. What's your biggest concern? You need it to hold water. You don't want it to break. there was a very famous failure on, I think it was Mulholland Dam. It's somewhere in the Los Angeles area where a dam was built, and then a few years later, the dam washed out. And so, of course, engineers, being scientists, they had to know, why did this dam fail so we don't do it again? And so they came and they examined all of the parameters they had done here. How many people know this story? When I taught intro to engineering, I always use this as an example. They checked everything to try to find out what had happened. And what they determined was, no, the dam was built with really good specifications. It should have never failed. The problem was those civvies. When they did their study of the surrounding material, they failed to note that the surrounding material was porous. So that as the dam filled up, the surrounding material then filled with water, got soft, and the surrounding material broke away, taking away what was holding the dam in place. So there's a lot of physics that goes into something like this to make sure that that baby's not going to break. Now, for this level of class, all we're going to do is calculate a few things. We're going to calculate how pressure changes with depth, and we're going to calculate the torque caused about the top and the bottom of the dam, so we can think about how you can hold it in place. So first, let's just do the pressure. So dP, now remember, the equation that we worked out for general physics was the pressure difference was equal to the density times acceleration of gravity times the change in height. Well, calculus, what do you do to change that? You just change a delta into a d, because delta means a finite change, d means an infinitesimal change. In truth, as I mentioned before class, the density really does depend on the depth. The density of water is not constant, it's compressible. When the pressure gets higher, the density increases. So if you actually are making a really deep dam, it doesn't have to be that deep if you think about it. Just going down 33 feet, you've doubled the pressure on the water. So when you're making the dam, that is something to consider, but for our purposes, we're just going to treat the density as a constant. So I have a dam. It has some depth, and I'm going to use capital, well, D is a poor variable to use when you're doing calculus, isn't it? So I will use H for the depth. And I'm going to set my coordinate system actually, let's not even worry about that direction. So my X is a measurement of depth. So X is going to be positive going down and 0 at the, whoops, took out the wrong thing. 0 at the water level of the dam. So I've got to define what my parameter is or I'm going to be in trouble. So now if I want to calculate the pressure, dP is equal to rho g dx. Going from the top to the bottom, what's the x at the, well, actually I should ask you, what's the next step once I have that equation if I want to find pressure as a function of depth? I have to integrate both sides, right? It wasn't a tough question, just to make sure that we're all involved. What should my limits be for pressure? It's going to start at atmospheric pressure, right? That's what's going to be at the top. And what about lower down? Whatever it is, right? So I'm just going to put P final and then later, like we've always done, drop off the F. What about for my X? What's the starting X? 0. And what's the final X? Okay, X final. And so now the integrals are, like I said, it's real simple. Integral of dP. Anybody else sweating a whole lot here? There I put the limits in. the pressure final minus pressure atmosphere is equal to rho g x final minus 0. And so the pressure at any depth is easily calculable. Now let's go a step further, something I didn't have shown. How can I find the force that the water puts on the dam? A what?
Pressure times area.
Okay, so force is pressure times area, but the pressure is continually changing. So since the pressure is continually changing, how am I going to find the total force? I have to break it up into little areas and add it up. That was perfect. So I'm going to take my dam, and my dam is, of course, this rectangle that should correspond. Come on. There we go. To the height of the dam. And I'm just going to take this and say, okay, I'm going to make a little piece that has a height of dx and a width of whatever the width of the dam is. And so what is my little piece of area going to be? So my dF is going to be the pressure times the width times dx. I've just calculated my equation for the pressure by integrating the rho g dx. And so I'm going to use that answer I just determined to say this is equal to rho g x times, so that's the pressure, times the width times dx. So now if I want to find the total force, what do I do to this equation? I integrate both sides. So I'm going to have the integral of dF going from, I'm going to start with 0 force in the dam to the force total, that's a T total, is equal to the integral from, again, x equals 0 to the height of my dam, h. There I took everything that's not x, everything that's a constant outside the integral. That's not a hard integral, right? So we can all just do that pretty much in our heads, x squared over 2 with my limits from 0 to h. So that's rho g w h squared over 2. And that's equal to the force total. Now, if you look at that force total, you could have done this without calculus because my pressure was linearly increasing with depth. If it's linearly increasing, I could have just taken the average pressure, which is the pressure at the... Oh, I forgot one thing in my calculation, didn't I? What did I forget? Atmospheric pressure. I did a gauge pressure. Is that legit? Kind of. If I want to know the net force on the dam, the backside has atmospheric pressure pushing back, and this gives me the net force due to pressure. But if I wanted the total force just from the water pressure, I need to include that. If I'm worried about, well, this would not be the right thing. So I will stop at that. I was going to say, if I was worried about the ultimate strength, then I need to use the pressure, the absolute pressure. But the ultimate strength wouldn't relate to the total force in the dam. It would relate to the force on some piece. So this here is the net force due to atmosphere. And you can get it just by taking the pressure at the bottom plus the pressure at the top and dividing by 2. So pressure at the bottom, the gauge pressure is rho GH, pressure at the top, gauge pressure at 0. Add those together, divide by 2, and you have rho GH over 2. Then multiply it by the area, which is the width times the height, and you get that equation. So we could have done it without calculus, but it's easier doing it with calculus if you know the calculus. So we're able to calculate the net force caused by pressure. What would be different if I had used the absolute pressure to get the total force? I would have had plus pressure atmosphere. All right, let me change color. I would have had plus pressure atmosphere. Whoops. Right there. And so I would have two terms. Pressure atmosphere times the width is constant. So integrating that would just be pressure atmosphere times width times height. And so that's a simple addition. The force that the atmospheric pressure is a constant, so that's why you don't have the 1/2 times the area. Any questions about these calculations? Gabriel?
When we're talking about area, are we talking about the area of like the surface of the water or the area that's pushing against?
The area that's pushing against. This was flipped sideways, so you're looking at the width of the dam. And so this edge here corresponds to what we're seeing there. And then this is way back behind it over there. Right, so this is a front view, and this is a side.
Oh, okay.
Sorry about that. I should have made it more clear. Okay, let's go to things that are more interesting. The torque. Come on. Oh, yes. I have to actually add pages. I forgot. I set this up with only 2 pages. Insert. I don't know how many, so we'll just put a lot in. So now let's go ahead and calculate the torque. Notice we used these top 2 equations already. Torque is R cross F. So d torque, the torque caused by a little bit of force dF, is going to be R cross dF. So let's go and draw our dam again. So once again, drawing the side view of the dam. I have my dam that goes like this. We have height H for the water, and so I set X equals 0 if I'm going to do the torques about the top. So when I do it about top, I'm just doing about the, that's not supposed to be an F, it's supposed to be a T. I'm doing it about the top where the water level is. I'm going to have at some depth X a force dF that goes into the surface. What is my perpendicular lever arm at that point dF? It's going to be R equals X. Somebody said that, so I went with it. Notice they're perpendicular. So when I do a cross product, I'm looking at only the perpendicular parts. These are already perpendicular. Thank you. Thank you very much. Now for this one, I am going to use the actual full-on pressure that is using atmospheric pressure as well. So I'm going to say dF is equal to pressure times dA is equal to pressure atmosphere plus rho gx times width times dA. And I had R is equal to X. So torque, magnitude, so I didn't put a vector sign, so it's just magnitude, is equal to the integral of R cross F. So that's going to be X whoops, that was a So there's my torque. What direction will this torque be? Given my picture, what direction will the torque be? Okay, R cross F is coming out. That's correct. Because I had to put my index finger in the direction of R, which was down, middle finger in the direction of the force, which was to your right. Your thumb comes out of the screen toward you. So it's a vector, but here I'm just doing the scalar calculation. I use the right-hand rule to get the direction. I have two terms, so I'm going to break this up into two integrals. P atmosphere times W, integral of x dx going from 0 to h, plus rho g W, integral from 0 to h of x squared dx. So if we do these integrals, what do I get for the first integral? Let's go ahead, because the limits are so simple, it's 0 for one of them, and we don't have exponentials or anything.
It's h squared over 2.
Okay, so I'm going to have P atmosphere W, the constants, multiplied by h squared over 2. And then what about the second one? That's the plus sign, surprisingly.
H cubed over 3.
So that's the total torque that's going to be created by the water on that dam, assuming my nice straight dam face. Remember, we saw in the actual dam, they constructed it with that clay, changing some angles so that they would actually be able to get a slightly different result on this. So that's a fair amount of torque. And if I look back, by the way, I'm now to the end of the lecture. Kind of short lecture, isn't it? If I look at this picture and I can't, come on. I totally can't zoom in or out now. Well, if we look at the picture on the left, that's the one that matches more of what we have. Actually, I do have one more calculation for that. This torque is coming out of the board, so I would need a torque that is going, or out of the screen, so I need a torque that's going into the screen to counter that, to keep this thing from rotating out, right? Because it needs to be in equilibrium. You need to have the net torque about any axis is 0. So where could I put forces to try to counter this torque that is coming out of the screen? There's one that's already there, and that's the force of gravity. Force of gravity, you take your radius from that force, the radius that I tried to find the center mass. The radius vector goes like this. So you take your fingers, the right hand, like this, and then down. That's going into the screen. So that's a counter torque already. How could I increase the magnitude of that counter torque?
More mass, because the force of gravity is on mass.
Okay, more mass, yes, but there's another thing about where that mass is placed. Where's it going to be more beneficial to have the mass placed? Further out. Because the perpendicular radius is the radius that's going in the horizontal direction because the force of gravity is down. So if that mass is further out, it's going to create a bigger counter torque to help compensate. So a reason to have it slope away is so you can get that counter torque there. What else can we do? Well, that's why they have that. That's going to make a force going that direction. Now you have your radius is straight down. This picture. Radius is straight down. Force is that direction. Again, it's going into the screen. So that's creating a counter torque. And between those, and of course, air pressure, which is pretty much going to cancel out the air pressure component from inside, you need to have the net torque being 0. There are things that will work against us, like, the force normal pushing up works against us. Did you have a question? Okay. So I've done a calculation of the net torque. What if I want to do the calculation of the net torque from the bottom, about the bottom instead of about the top? What would I have to do differently? I do what? Okay, the limits. Because if I did it about the bottom, then I'm going to be going from the bottom to the top. But there's another piece there. The equation for the pressure is going to be the smallest at the top, the largest at the bottom. I'm going to have to, unless I use, I usually would redefine x equals 0 at the bottom, so my r is equal to x. If I keep my x defined as x equals 0 at the top, then my perpendicular distance is going to be h minus x. So that's the real key, is you're going to have to change either the pressure either the reference point of where x is, in which case the reference or the pressure equation is going to shift from x to h minus x, or shift what the r perpendicular is if you keep the same reference point. So if I did it about the bottom, I'm going to keep the same axes. Well, axes, plural. I really only use one, so let's make it singular, axis. So what's going to change is the r perpendicular is going to be h minus x instead of x. And my pressure equation will be the same. And so my torque I forgot to put the R part. I just put in the force part. Let's shift this over so I can fit the R part in. Well, this integral is more interesting, isn't it? Because when I multiply through, I'm going to have 3 terms. Four terms, would you believe? So yeah, that's 4, not 3. So now I have to integrate these. There are 2 of them that are linear in x, one that's squared with x. So what I'm going to get is, and actually I'm still going from 0 to h. I'll still integrate from the top to the bottom. So I have those 3 terms, or 4 terms, 3, depends on how you want to count them since I combined 2, for my torque about the bottom. More complicated simply because we're calculating about a different location. Now, just to be clear, what direction is this torque about the bottom? This one's going into the stream. Because my R is now going up, force is still into the dam, that's into the stream. And so now I would need torques in the opposite direction. If you look at these 2, it seems really confusing because I had about the top a torque one direction, about the bottom a torque the other direction. But if it's in equilibrium, the sum of the torques has to be 0 about any axis. And so the actual information you get out of this is going to be the same in terms of where I need to put my forces to create the counter torques. That really is the end of what I have planned for today. no fluid flow. We haven't started talking about Archimedes, or not Archimedes, about Bernoulli principle yet, so that's all I have. You guys got questions?
The first term,
Yes.
how?
I got the h squared because the integral with respect to dx is x. Putting in my limit, that's going to be an h.
Okay.
Yeah.
Board.
All right. Given that I finished 20 minutes early, I did have time to go ahead and go through that. I should have done it. Anything else?
Can you show the torque one more time for the force of gravity and for the other mass that you were showing on the dam?
Okay. So torque's about, let's say about what location first?
The top.
Okay. So torque's about the top. I'll just go to another page. And draw forces on this, and then we'll calculate the torques from each one, just direction and, So we had a force here, I'll call a force buttressing. We had a force of gravity here. We had the dF there that we integrated because it was changing. And then, of course, we also have forces from air all along there. So those are the forces that we need to consider. So for each one, we have our equation that says torque vector is equal to R vector cross F vector. So let's just go through these individually. Some torques about here. So if I look at the one with the water on the dam, my R vector is pointing down. The force vector is pointing that direction. So that means I take my right hand and I need to have index finger pointing down and middle finger pointing to the right. And so down, and of course, if I turn like you and go to the right, then my thumb comes up. So that's the force from the water. Then let's go to gravity. So now for the gravity, my R vector is something like this, right? It's at an angle. And my force is down. And so now I take my same right hand and I put my index finger like that, middle finger like that. And so once again, I got to turn like this to do it the same as you. And yeah, that's it. Okay. It's into. I was thinking it was supposed to be out. And I was like, wait, what? So that's into the screen. Now, remember, it's the perpendicular part is all that really matters. And so oftentimes we actually will approximate this and say, okay, or not approximate, but redraw it. And say that R vector has two components. This one that's here is parallel to the force and it's not going to contribute to a torque. And so it's only this perpendicular part that contributes. So all we usually do is we measure, or often all we do is we measure this. And we say that's our perpendicular lever arm, R perpendicular. And so that's why I was saying what really matters to increase that torque is getting the mass further away so that perpendicular lever arm is larger. Then the third one, the buttress. we have R is again going something like this, but now the force buttress is going that direction. So again, I'll have my index finger like this. Index ends with an X. My middle finger like that. And so taking the right hand, boom, boom, in. And last of all, we have that air pressure. Now for the air pressure, it's acting all over this, and our R is going to be going from our pivot point to where each one is. But for each case, you can see that the R is the same direction as we had in the last two, roughly speaking. And then the force is somewhere between that of the buttress and the gravity, down and in. Both of those directions give you into the screen. And so the torque that's caused by the air on the outside is also going to be into the screen. Did that answer it for you?
Yes.
Other questions? Okay, then I'll see you in just under 2 hours here.